Hey guys, Mr. O'Sullivan here. Hey, we're going to go over the worked out solutions for AP practice exam number 3. All right, so let's go ahead and let's dive in. Okay. All right, so question 1. The velocity of particle A moving along the x-axis is given by the function VA at t, is shown in the graph above, where VA at t is measured in meters per second and t is measured in seconds. A second particle B also moves along the x-axis so that its position, SB at t meters, and velocity VB at t meters per second for the closed interval from 0 to 10 are differentiable functions with selected values shown in the table above. The velocity VB at t has exactly 2 zeros on the interval from 0 to 10. Okay, I'm going to highlight that because that is going to mean something here in just a little bit. Okay, I also want to just remind myself that the graph relates to particle A. So I'm just going to kind of label that. So if I'm talking about particle A, I'm looking at the graph. And if I need to get information for particle B, I'm looking at the table. Okay. And then I'm asked to do a few things. First off, it asks, is the speed of particle A, so I'm talking about particle A, increasing or decreasing at time t equals 6, and explain. Okay, well, what I should look at to determine whether the speed is increasing or decreasing at a particular time is I need to look at the sign of the velocity and the acceleration at that particular time. So I'm really looking for V A at 6, and then also the derivative of velocity or acceleration. I'm just going to put V prime at A at 6. And what I want to know is what the signs of those two values would be. The signs are the same, my particle, the speed is increasing. If the signs are different, the speed is decreasing. Okay, so I'm looking at, this is again for particle A. And so I'm going to go to the graph to find the value of VA at 6. And so all I care about is, okay, here's 6. And I can just see that, hey, my velocity is a negative value. It's below the x-axis. I'm just going to kind of say, all right, VA at 6 is less than 0. Now, to get the acceleration, what I'm interested in is the slope of the tangent line at that point on my velocity function. So I'm looking at this sketch a tangent line. All I care about, what's the slope of that tangent line? Tangent line's going up, it's a positive slope. So that means acceleration at time 6 for particle A is positive. My signs are different. Signs are different. Therefore, what's going on with speed? Speed is decreasing. Speed is decreasing at t equals 6. And that is my explanation. Okay? All right. Part B. For how many values of t over the closed interval from 0 to 10 is the speed of particle A, again, I'm talking about particle A, equal to 1 meter per second? Justify your answer. Okay. I'm looking at speed for particle A, and I want to know how many t values in that closed interval from 0 to 10 is the speed equal to 1 meter per second. Okay. All right. Well, I'm going to look at, again, my graph of velocity for particle A. And I'm looking at the speed. So the speed, I remember, speed is equal to the absolute value. So this would be really the speed for A, absolute value of the velocity for particle A at t. So in order to look at that on my velocity function, I can basically just do a vertical reflection whenever my velocity dips below the x-axis where it's negative. So I'm just going to like kind of show this. And now I'm just going to redraw the velocity function. And I can kind of see right here, I know that this is going to dip up, come up like that. I'm basically just kind of reflecting that. And I know, so now that point down there on the speed graph is at 5.5, comma 1. And then also this portion right here is going to reflect up like that. So that, I just kind of like trace that in red. That red function would now be speed of particle A at t. Okay. Well, now what I'm asked to find is, okay, how many t values does that speed function have a value of 1? Okay, so I'm looking at 1. I'm just basically looking, when does it cross? Well, there's 1 right there. And then again, there's another one right there. So I'm going to say my answer there are 2 values of t where speed, I'm just going to call that the absolute value for A at t is equal to 1. Okay, and that's my justification. I'm basically just showing that speed is the absolute value of velocity by the graph, for examination of the graph. For exam of the graph, what graph? The graph of V at A at T. Okay, VA at T. Okay. Part C, find all times T on the interval from 0 to 10 at which particle A again changes direction. Okay. And for a change of direction, I'm just looking when velocity is going to change from positive to negative or negative to positive. So looking at my graph, I'm going to erase my speed, get it back to velocity again. And I'm interested right here, and right here. So it looks to me like there's 3 direction changes. And I don't have to say at what t values they occur. I'm just going to say, nope, I lied. It does say find all times t on the interval at which particle t changes direction. So I need to list those out. So that looks like that's at 4, 7, and 9. So the particle changes direction at times t equals 4, 7, and 9 because velocity of A at t changes from pos to neg or negative to positive at those times. Okay, I have to say both positive to negative or negative to positive. Okay, sweet. All right, picking up steam. Part D, find the total distance traveled by particle B from time t equals 0 to time t equals 5. Okay, we are changing gears now, and now we are talking about particle B, so I'm going to be looking at the table. I want the total distance traveled by particle B from time t equals 0, time t equals 5. I'm going to just copy that table down below. Don't try to stop me because you're not going to be able to do it. Copy in the table. Oh. Okay. So there's my table. And what I'm interested in is the total distance. Okay, so for the total distance, what I'm going to be looking at is the middle column. That is my position for particle B at certain times t, these times t here in the first column. And so I'm going to kind of ignore, I don't care about that velocity column. So what I want to do is I want to just look as we go from each time here. So from position 2 to position 6, that's a change of 6 units. We go from 8 to 12, that's 4 units. 12 to 15, that's 3 units. Now here's where I want to be careful. I go from 13, I'm sorry, from 15 to 13. Well, you'd say, well, that would be -2. But again, since I'm going to be talking about total distance, I want really kind of like the absolute value of -2, because I don't care about direction. I don't care that that would have been 2 units to the left. I just care that it moved 2 units for total distance here. So I'm treating that as 2. When it goes from 13 to 12, that's the same way. It's -1. I'm going to treat that as 1. From 12 to 12, it doesn't move. And then from 12 to 18, that's 6. So my total distance is just going to be 6 plus 4 plus 3 plus 2 plus 1 plus 6. It's a numeric answer. Don't bother adding that up. It'd be foolish to kind of lose a point because we couldn't do made a simple adding mistake. Okay, part E, find the average velocity of particle B, again, still talking about particle B, on the interval from 0 to 10. And we want to include the units. Okay, well, we are going to be looking at the table again. So let me just bring that table. Okay, now to find the average velocity, what I want to do, I'm looking at on the interval from 0 to 10. So I'm interested in right here and right here. Okay, average velocity. It's not the average rate of change of velocity, but the average velocity. Okay, that average velocity is going to be equal to, and what I want is I want SB at t minus SB at 0 over 10 minus 0. Okay, average velocity is equal to my average rate of change of position. Okay, can't leave my answer like that. It's not a numeric answer, so I just got to go here. And SB at 10 is 18. SB at 0 is 2. So 18 minus 2 over 10 minus 0. That's a numeric answer. I'm going to leave it like that, but I do want to include units. Well, I know my units for position. Double check back to my position is given in meters, and time is given in seconds. Yep, T is measured in seconds. So that's going to be meters per second, and that makes sense. So meters per second are the units that go with that. That makes sense for average velocity. Okay. Part F, over the closed interval from 0 to 10, find all times t during which the two particles travel in the same direction. Okay, well, I'm going to need the graph and the table to do this one. So actually what I'm going to do, since I've got it right up here, I'm going to do my work for this one up here. Okay, well, I can look at, for particle A, I just know that when velocity is positive, the particle is moving to the right. So it's moving to the right. I'm just going to do in blue to indicate the particle is moving to the right. So on that interval there, I'm just kind of highlighting on the x-axis, from 0 to 4, particle moves to the right, and then it moves to the right from 7 to 9. Okay? And then when velocity is negative, the particle is moving to the left. So it's moving to the left on the interval from 4 to 7, and then also from 9 to 10. Okay, and that was particle A. Okay, particle B, I'm looking at now, I want to look at the velocity column, because that's what's going to indicate which direction my particle is moving. And so if velocity is positive, it's going to be moving to the right. So I'm seeing here, I've got positive values until I get to the 0. And so it's moving to the right. And that would be, better be consistent. I said moving to the right. I'm going to use blue just to indicate that. So where it's positive, so velocity is positive, and it's moving to the right. And that's going to be my interval from 0 to 3. Okay. Now, this is where it's important when they told us the velocity for particle B has exactly 2 zeros on that interval. Okay, well, here's my zeros. There's a 0, and there's a 0. That means in this interval right here, from time 0 to time 3, that my velocity never goes negative and then comes back positive. Okay, at like one of these times in between like 0 and 1. You know, velocity is positive 4 at time 0, and it's positive 2 at time 1. Well, because I know there can't be a 0 in between time 0 and time 1, velocity must not have gone negative. Okay, so that is why they kind of added this sentence that velocity for B has exactly the 2 zeros that are shown in the table on that interval. Okay, so then we can kind of just say, hey, on this interval here from 0 to 3, velocity is only positive, and we can therefore know that the particle is moving to the right. Okay, and then again, it's also only positive down here in this interval from 8 to 10. Okay, so moving to the right again, and then in this intermediate interval right between here, particle, the velocity is negative, particle is moving to the left, and that would be on the open interval from 3 to 8. 3 to 8. Okay, well, here's what I'm going to do. I'm just going to, on the graph, I'm kind of just using the graph of the velocity of A just for a number line purpose. And so right here on y equals 1, I'm just going to kind of show what I've got here. So from 0 to 3, 0 to 3, I'm putting that blue line that indicates this is particle B I'm putting right here. Okay, and then it's going to change. It's going to be red from 3 to 8. 3 to 8, and then it's going to change back to blue, meaning that it's moving to the right from 8 to 10. Okay, so now I'm comparing those two lines, and I just want to see where I have an overlap of the same color. So it looks like it's moving to the right at from 0 to 3. So it's moving the same direction over that interval. And then it's also moving to the left over that interval from 4 to 7. And then it's also moving into the right on the interval from 8 to 9. Okay, so those three intervals, 0 to 3, 4 to 7, and 8 to 9, 0 to 3, 4 to 7, and 8 to 9 are the times where my particles are moving in the same direction. Okay? All right, so part G. On the closed interval from 8 to 10, which is greater? The average acceleration of particle A or the average acceleration of particle B? Give a reason for your answer. Okay. Well, let's see. The average acceleration of particle A. So average acceleration of A, that's going to be given by the, on the interval from 8 to 10, that's going to be given by velocity of A at 10 minus the velocity of A at 8 over 10 minus 8. Okay, and then corresponding fashion, average acceleration of B is going to be exactly the same, but it's going to be the velocity of B at 10 minus the velocity of B at 8 over 10 minus 8. So then really all I've got to do is I've got to kind of drop in the function notation here and figure out what those velocities are. So let's look at the velocity of particle A first. So VA at 10, I'm looking at the graph. So I need to know the velocity at 10. Okay, so my velocity at 10 is going to be, I guess, maybe even an easier way to look at this would be on the, I can really draw a secant line that's going to go from my endpoints. And so that, the slope of that green line that I just drew there, that's a secant line that goes through my endpoints. Okay. That is given, that slope is my average acceleration over that interval. Just want to make sure, check my interval. Yep. Oh, no, 8 to 10. Check that. Sorry about that. So actually, I don't want to go through that. I want to change this endpoint so it's going through eight. So I'm looking kind of like that. Okay. So that slope of that line, that's my average acceleration on that interval from 8 to 10 for particle A. Okay. What I could do is I could, for particle B, what I'm going to do is I'm just going to plot those points on my graph. And again, I'm looking for basically 8 to 10, and I'm looking at velocity. So when I'm at time 8, particle velocity of particle B, the velocity of particle B is 0. So that would have a point here. And then at 10, the velocity is 5. Whoa. So that means at 10, not at 9, but at 10, at 10, the velocity is 5. Okay, so then if I draw a secant line through those points, I can easily see that the average acceleration for particle B is greater. Okay, obviously this is a, some positive slope, steep positive slope, and also that is a negative slope. So I'm basically going to say particle B's average acceleration is greater. Okay, and my reason is basically what I've kind of set up here using my values for my velocity. Okay. Okay, part H. Is there guaranteed a time t on the interval from 7 to 10 such that the acceleration of particle B is equal to 2? Justify your answer. Okay, as soon as I see, is there guaranteed a time, I'm thinking, hey, it's a theorem. So it's a theorem question. They're basically kind of testing me on a theorem. Now I got to determine, is it intermediate value? Is it mean value for derivatives, mean value for integrals? You know what? Well, is there guaranteed a time t on the interval from 7 to 10 such that the acceleration of particle B is equal to 2? Okay, because I'm seeing acceleration. And then for particle B, I'm going back to the data that I'm given for particle B. And they give me, what do they give me for B? In table, they give me the position, S be a t, and they give me the velocity, v be a t. Okay, so that kind of clues me in. I'm not given acceleration. And so since I don't have the same quantity in that I'm given in the data and that I'm asked about in the question, but it's like the derivative of velocity acceleration. So I'm like kind of one derivative away. I'm thinking mean value theorem for derivatives. Okay, which would mean if I know that one, I'm going to just kind of write it in the context of this problem. I'm basically saying because, so I'm changing my conditions from if to because. So I'm going to say because v b at t is continuous on my interval 7 to 10, and because v b at t is differentiable on my open interval 7 to 10. Hey, I better make sure that's true. Well, so I'm looking here, again, talking about the velocity of particle B, and okay, good news. Second paragraph here, second particle B also moving along the x-axis at its position, s be at t meters, and velocity v be at t meters per second for the closed interval 0 to 10 are differentiable functions, okay? So I'm good to go. They told me it's differentiable, therefore it's continuous. I do have to mention that in my answer, okay? So I've met the two conditions necessary for the mean value theorem for derivatives, okay? I never need to mention that in my answer. I'm just going to say because these two conditions are met, then there is at least one, okay, and it's a t value this time. There is one t that's going to be equal to some c value such that, big finish now, such that what? Such that the acceleration, which is going to be v prime of particle B at that particular time value that we're calling c, is equal to vb at 10 minus vb at 7 over 10 minus 7. Now that's got to be equal to 2. This whole hot mess, they're saying, is equal to 2. Okay, I'm almost done. What I have to do is just drop in my values for VB at 10 and VB at 7 and just make sure this works out to be 2. Okay, so VB at 10 and VB at 7. VB at 10 is equal to 5 and VB at 7 is -1. Okay, just pulling those right from the column, from the table there, 5 and -1. So this is 5 minus -1. And the good news, 5 minus -1 is 6. 10 minus 7 is 3. 6 divided by 3 is 2. We're good to go. Awesome. Okay, that was part H. That was all of question 1. All right, now we kind of get to kind of a more FRQ, kind of like the length that we were used to working all year long. So we're given another graph. So the graph of g at x is shown above, along with the line tangent to the graph of g at x equals 0. Okay, so that's the blue line, is that tangent line. Let f be a differentiable function defined by, so they're kind of giving us the graph is g at x, but now here's another function, f of x, that is equal to root 10 minus g of x. Okay. All right, part A, write the equation of the line tangent to f of x at x equals 0. Oh man, we can do this all day long. So we're going to start with point slope form. Okay. And I know x is 0, so x sub 1 is 0, x minus 0, I'm off to the races. I know m is going to have to be equal to, well, it's tangent to f, so it's got to be f prime at this particular x value. So m is going to be equal to f prime at 0. So I got to get that. And then I also know that y1, so this is f prime at 0, and y1 has just got to be f at 0. Okay, well, I take care of, those two items there in function notation, just get the values for those, and I'm done. So let's look at the f at 0. I can basically go back to my definition of f of x, which is right there. I'm just going to copy that down below. So there's f of x. And so really, I want f at 0. So f at 0 is equal to the square root of 10 minus g at 0. Okay, well, now I got to find g at 0. So I got to go to the graph. G at 0, there's 0. G at 0 is equal to 1. Okay, so this becomes 10 minus 1. It's 9. That's equal to 3. So f at 0 is equal to 3. So y minus 3 is equal to, okay, now I need f prime at 0. So I got to find, before I can find f prime at 0, I got to find f prime at x. Okay, so here's f of x. I'm going to do a rewrite on the fly. Going to make my radical just to the quantity raised to the 1/2. And now f prime of x is going to be equal to, power rule, 1/2, quantity 10 minus g at x. Got to remember to subtract 1 from the 1/2, so that's going to be negative 1/2. And then don't forget, times chain rule, right? Times the derivative of the inside function, which is going to be times negative g prime at x. Okay? Now I want f prime at 0. So that's going to be equal to 1/2 times 10 minus g at 0. Well, g at 0, I just found out there, that's 1. To the negative 1/2 times negative g prime at 0. Okay, so let's see. Now I got to figure out what is g prime at 0. Well, what I'm going to use to find that is the slope of my tangent line at x equals 0. So I just got to figure out, hey, what's the slope of that tangent line? Well, good news is I got a point there. I got a point there. I'm going up 1. I'm going to the right 2. Slope of that line, m is equal to 1/2. That is g prime at 0. Okay, it's a little tricky. That's kind of why they gave us that tangent line, and that's also why it kind of like cuts through the corners on our graph there. So I'm going to drop that in. Now that is going to be negative g prime at 0, so that's negative 1/2. So that's negative 1/2, and then I've just got the rest of this 1/2 times the quantity 10 minus 1. That's going to be 9 raised to the negative 1/2 power times negative 1/2. Okay, I'm not going to take any chances. I'm just going to rewrite that. I'm going to simplify it because who really knows what 9 to the negative 1/2 is anyway. So I just got 1/2 times 9 to the negative 1/2. I know you guys know it. Times negative 1/2 times the quantity x minus 0. Okay, that right there is the equation of my tangent line. Okay, awesome. Okay, part B. Part B is a little salty. It says let g at 2 equal a. All right, it's not too bad. And then It says evaluate this definite integral from 0 to 2 f of x times g prime of x dx. Express your answer in terms of a. Okay, so our answer is still going to have a variable in it floating around as a. Okay, this one, yeah, this one's a little salty. Well, here's what we can do. Let's take our definite integral, 0 to 2 f of x g prime of x dx, and we're just going to do a rewrite. And the only rewrite is we're going to substitute in what f of x is defined as. So this is going to be the definite integral from 0 to 2, and instead of f of x, we go up here, we had it right here. F of x is equal to the square root of 10 minus gx, okay? See it right there, I copied it down from above. That's in the stem of our problem. So that's f of x. So I'm just going to write what that is. The square root, I'm going to leave my rewrite. So the 10 minus g at x raised to the 1/2 power, right? That's equivalent to radical 10 minus g at x times g prime at x dx. Sweet. Okay. Okay, so all we did, the good news now is at least our integrand just has like g of x and g prime of x in it. Okay. All right. This one, I'm spying here, this g prime of x is the derivative of this inside function kind of piece of my integrand. Okay, it's almost the derivative. The derivative of the inside function should be negative g prime at x, right? But we don't have the negative, we just have g prime of x. We see that? There's the negative. So if we took the derivative of, 10 minus g at x, we did ddx of that. ddx of 10 is 0. ddx of negative g at x is negative g prime of x. Okay, so we're kind of set up for success on this this integrand. So what I'm going to do is I'm going to come up with the antiderivative, my integrand, and really all I'm looking at is this first part of it. Well, it's kind of like the power rule in reverse. So it's going to be the quantity 10 minus g at x. Okay, now I'm integrating, so I want to add 1 to the exponent. So that's going to make it 3/2. Immediately, if not sooner, divide by 3/2. Actually, I could also, dividing by 3/2 is the same as multiplying by 2/3, right? So there's my 2/3. And then that missing negative sign, where I took the derivative of the inside function here, and it should be negative g prime of x. I don't have the negative, so I got to add that out front. Okay, so this is my antiderivative of that integrand. Okay, if I got time and I'm feeling kind of plucky and I'm not 100% certain, I could kind of like take the derivative of that, what's in red there, and I'm going to get my green integrand as my answer. Okay, awesome. So now I'm going to keep rolling. I'm going to bring over my bounds, 0, 2, and then I'm going to drop down to the next line, and all I'm doing is I'm taking my integrand FTC part 1, subbing in the upper bound minus subbing in the lower bound. So this is going to be negative 2/3 times 10 minus g at 2, everything raised to the 3/2, minus negative 2/3 times the quantity 10 minus g at 0, everything raised to the 3/2. That's almost a numeric answer. What I want to do is I just got to take care of that piece, g at 2, g at 0. If I can change those into values, I'm done. And I do not want to waste time trying to simplify that piece. Hey, the good news, what's g at 2? G at 2 is a. They told me that. So I'm just going to substitute in a for that. Just going to cross it out and write a there. You okay with that? Now g at 0, hey, I know that. G at 0, I've seen that before. G at 0, here it is right here when I was using that one. G at 0 is 1. Okay, that's on the graph. So g at 0 is 1. Crossing that out, I'm putting 1. I'm done. I'm moving on. That's my answer. It's kind of a little dodgy, maybe just crossing that out. I might rewrite it, but I'm not going to simplify it. I might leave it like that. Okay? That was salty. A little bit salty there. Yeah, baby. Salty. Okay. Next one. Evaluate the limit as x approaches 0 of f of x minus 3 over g at x minus e to the 2x, or show that it does not exist. Okay. Well, I don't know about you, but I almost smell that it's going to be like L'Hopital. But if it's L'Hopital, and even if it's, not, what I need to do to check this, I have to show that if it is L'Hopital, I first off have to show that I can apply L'Hopital. I can't just like jump off and like start taking the derivative, denominator, and come up with a new limit expression without showing that I'm coming to an indeterminate form. And this is importante. The way we have to do that is we have to break up and show two limit expressions, one for the numerator, one for the denominator. Okay, so the way I want to show it is this way. The limit as x approaches 0 of just the numerator, f of x minus 3. Okay, well, to do that, I would just plug in. So this is really going to be f at 0 minus 3. Well, what's f at 0? That's a great question. Well, I know, got it down here, there's f of x. So I can use that to find f at 0. Hey, I found that. I had to find that actually for, in part A, that's 3, right? There's my f at 0, there's 3. Okay, a lot of times, and again, since you're going to be compressed for time, you're already going to have like some values for these functions that you've calculated in prior parts of the problem. So f at 0 is 3, so this becomes 3 minus 3, whoop, that's equal to 0. So you've just shown that the numerator as x approaches 0 is 0. Okay, so now we're really kind of sniffing, hey, this is probably going to be L'Hopital. So now I got to show a second limit expression for the denominator. Limit x goes to 0 of g at x, just the denominator, minus e to the 2x. So that's going to be g at 0. Hey, I think I know what that is. Minus e to the 2 times 0. Well, g at 0, yep, I remember it right here. There it is. G at 0 is equal to 1. So I get 1 minus e to the 0 power is 1. Wow. So look at that. That also evaluates to 0. Okay. So that means what? That means like now I can apply L'Hopital. Okay. So what I would do, I've done this. I've evaluated the numerator separately, evaluated the denominator separately as two different limit expressions. I get the indeterminate form 0 and 0. And so now I just go a little LH, show I'm kind of using L'Hopital. And then I'm going to come up with a new limit expression. Just going to do down here. So it's the limit as x approaches 0. Okay. And I'm just going to show my work, d dx of f of x minus 3. Well, that's just going to be what? F prime of x minus 0. So my numerator on my new expression is going to be f prime of x. Okay, sweet. Over, now I'm going to do the same thing, d dx of g at x minus e to the 2x. Well, that's going to be what? G prime of x. That's not too hard. Minus exponential, that's not bad. It's going to be minus what? 2 e to the 2x. Okay, I hope you know where that 2 is coming from. That's my chain rule, right? Sweet. Okay, so that's my new denominator, g prime at x minus 2e to the 2x. Okay. I got a little excited. In the numerator, I should have just showed that as f prime of x. Easy, tiger. Okay, now I am going to plug in my, as x approaches 0, so I'm going to have f prime at 0 for my numerator. And then I'm going to also plug in the denominator, g prime at 0 minus 2 times e to the 2 times 0. Okay, well, the denominator, g prime at 0, seems familiar. G prime at 0. Oh yeah, g prime at 0, there it is. G prime at 0, that's 1/2. That's the slope of my tangent line. So g prime at 0, that's 1/2. And then minus 2, and then e to the 0 is going to be 1, so it's 1/2 minus 2. Okay, that is my denominator. And then, so I know right now I'm either at the end of the road. I can't use L'Hopital again because I'm not coming up with that indeterminate form where I have a 0 in the denominator. Okay, I got something other. I'm not sure what 1/2 minus 2 is, but I got something else. Now in the numerator, f prime at 0. Oh yeah, that's coming back to f prime at 0. I think I had that in part A for my tangent line, right? Ooh, went up to the wrong problem. F prime at 0. There it is, f prime at 0. Oh my gosh, it's that hot mess right there. Woo. It's all of that. That's 1/2, 9 to the negative 1/2 times negative 1/2. I can't remember that long enough to bring it down. So I'm just going to do this. I'm going to multiply the 1/2 and the negative 1/2. That's negative 1/4 times 9 to the negative 1/2. Okay, that is my f prime at 0. So I'm going to just bring that down below. Negative 1/4, 9 to the negative 1/2. Negative 1/4, 9 to the negative 1/2. Numeric answer, throw up your hands, move on to the next one. Okay, awesome. Okay, last part D. Is there guaranteed a value C in the interval 0 to 1.5 such that f prime of C equals 0? Explain. Okay, well, again, I hope, is there guaranteed a value C? You said, whoa, that's a theorem. This is a theorem problem. Which one is it? I would, the likelihood when they test you on a theorem, and again, you got just 2 questions, multiple parts for each, but not a whole lot of time. Mean value theorem for derivatives. I don't want you just thinking, oh, that's only what it's going to be, but I'm just thinking, yeah, better than a 50-50 chance, maybe. Specifically here, how I know it's probably going to be that is because I'm given f prime of C, and then if I go back, what am I given in this problem? I'm given, look at that, f of x. So again, I'm given f of x, and then in the problem it talks about f prime, the derivative. If it was the same, if like part D would have just said, is there guaranteed a value C on the interval 0 to 1.5 such that f at C is equal to 0, and I've got f of x given in the problem, I'm thinking IVT, intermediate value theorem. But because it's, the function and its derivative kind of one away like that, I'm pretty sure it's MVT for derivatives. If that's the case, I'm going to start my explanation as the conditions are met. So I'm going to just say, if it's MVT, that's what I'm banking on. I'm going to say because, instead of if, I'm saying because. Well, because what? Because the wonderful things he does. Because of f of x is continuous on the interval 0 to 1.5, closed interval, continuous closed interval 0 to 1.5, and f of x is differentiable on that open interval 0 to 1.5. Okay, so those are my conditions that have to be met. Are they met? I don't know. Let's go back and see. So I'm looking up here. Hey, look at that. Yay. Let what? Let f be a differentiable function defined by that. So they're telling me it's differentiable. They tell me it's differentiable. I also know it's continuous. Sweet. So I've met those two. Because of those two, then here comes the conclusion. Then there is at least one what? One x equal to c such that, ooh, I'm getting lazy in my old age. I should say it's what? 1x equal to c in that interval 0 to 1.5 Sorry about that. I'd have to lose a point in there. Now we're ready for the such that, and the conclusion for MBT, the equation, is going to be that f prime at c is equal to f at 1.5 minus f at 0 over 1.5 minus 0. Okay, and this whole shooting match has got to equal what value? It's got to equal 0. Okay, so that means I can't stop there. I got to find my values on my function notation here. So I'm going to look at what's f at 1.5. Well, here's where I'm using my, what's f of x? F of x is equal to the square root of 10 minus g at x, right? That's what f of x was. There it is. F of x is equal to the square root of 10 minus g at x. Okay, so f at 1.5 is going to be f at 1.5 is equal to the square root of 10 minus g at 1.5. Okay, well, to find this, I got to go up to my graph. G. Hey, look at that. Woo. G at 1.5 is equal to 1. So that's 1. So that's the square root of 10 minus 1. That's the square root of 9. That's 3. So f at 1.5 is equal to 3. So that's 3. F at 0. Wow, I've seen that before. F at 0. F at 0. There it is. I got f at 0. I calculated that there. F at 0 is equal to 3. Yep. So that's going to do it. So I'm going to get 3 minus 3, that's 0, over 1.5, that's equal to 0. Boom. Game, set, and match. We're good to go. Okay. All right, guys. That's all of that one. I hope that helps. Okay, guys. Thanks for your efforts. Keep up the great work.